Hi, in this video I would like to share what I learned about dimensionality reduction, stochastic neighbor embedding, and t-distributed stochastic neighbor embedding, which is a variant of SNE. So first, let's understand the concept of this dimension. So let's have a data point which will have two attributes, x and y. So x can represent the age and y can represent the population count. So we can now plot a 2D graph which will have all these data points. And here, the point here can represent, for example, the population with age equal to 23 and the count equal to 1.8 million. So now let's have a data point with three attributes instead, x, y, and z, and they can represent age, population count, and height of the population respectively. So now we will need to plot a 3D graph to represent these data points. And now the data point here can represent, for example, the population with age 23, count 1.8 million, and height 170 centimeters. Let's add one more attribute W, which will represent the weight of the population. Can we plot this now? No, since there are four dimensions. We need to transform this data in order to plot it in 3D. So for that we need to somehow reduce the number of dimensions so that the transformed data correctly represents the original data. So dimensionality reduction, it consists of techniques to transform higher dimensional data to lower dimensions such that the meaningful attributes of higher dimensions are retained in the lower dimensions. So it kind of tries to create a mapping from higher dimensions to lower dimensions. And why do we need this dimensionality reduction? So first one is to eliminate the problem of curves of dimensionality. So if there are too many dimensions, it is very difficult to generalize a solution. Then if we want to select a few attributes out of lots of attributes, that is, we want to select the ones which are important. If we want to make visualization easy, then also we can use dimensionality reduction. And also, if we have sparse high dimensional data, then it is difficult to find patterns in there, and also it is difficult to group the objects together. So if we want to make that process easier, then also we can use dimensionality reduction. So stochastic neighbor embedding, it is a DR technique that preserves neighborhood identity. So if two points were in neighborhood of each other in higher dimension, then it will retain that in lower dimension as well. It is based on similarity of data points. So we use affinity as a measure of similarity, which is nothing but scaled squared Euclidean distance. So for each n-dimensional data point, there is a Gaussian centered around it. This is an n-dimensional Gaussian, and the probability density under this Gaussian defines the probability distribution over all potential neighbors. So if we have three data points, 1, 2, and 3, and if we want to use point 1, for example, then we can create a Gaussian centered around 1, and we can calculate the probability density using this equation for f of x centered around a. So in this equation, a is the center of the curve, b is the standard deviation, x minus a is the Euclidean distance, and we square it, so it's squared Euclidean distance. B is also squared, so standard deviation squared is basically variance. I will explain later how to set this variance. And then we calculate the probability of 2 being neighbor of 1 as f of 2 divided by f of 2 plus f of 3, and this is all centered around point 1. So the aim here is to approximate this distribution so that the operation that we are going to do, for example, if we want to run clustering over this data, then we can do this using low dimensional images and we should see the same or similar results. So there's an example scenario where we want to group thousands of handwritten digits. So we can first reduce the dimensions using SNE. So in this case, it can create lower dimensional data based on skew, orientation, and stroke width. And then we can use this lower dimensional data for clustering and we should see the correct results. So let's have a look at the SNE algorithm. So first we find P of xj given xi, that is the probability that xj will be a neighbor of xi. For this, we need to set the variance as we discussed earlier. So you can do it either manually by hand or use binary search such that the entropy of the distribution that is equal to log of k. This is log to the base 2 of k. and where this k is the perplexity or effective neighbor count. So you choose a value for perplexity, for example 10, and you can choose a range for binary search, for example between 1 and 1000, and then you compute the midpoint, which is around 500, and you calculate this p of xj given xi using this 500 as standard deviation, and then you find the perplexity using its formula and see if it matches the chosen value for perplexity. Then we have to set some initial solution, this y0, and you can set it to random values, and here the n is less than or equal to 3. So this is like the lower dimensional image. Then we repeat for several iterations. So you can choose the value of this uppercase T to, for example, 1000. And what you do is you first compute this probability matrix Q, Q of yj given yi. That is the probability that yj will be a neighbor of yi in lower dimensional image. So this is also again a Gaussian neighborhood, but only in this case the variance is fixed, that is equal to zero point 0.5. Then we compute the gradient d, because this is a gradient descent algorithm. So for that we require a cost function. So we can the cost function is the sum of Kullback-Leibler divergences. Then we update this initial solution based using this equation here, and the momentum here, it is basically required in order to avoid the poor local minima during gradient descent. So let's see some problems with SNE. So first, it's difficult to optimize and you must run it several times to find appropriate values for parameters. And because of that, it's computationally expensive. There is also something called crowding problem, which states that the area of 2D map to accommodate moderately distant data points will not be large enough compared with the area to accommodate nearby data points. So that means since the map size has reduced, so far apart points in higher dimensions may not be that well separated in lower dimensions when compared with nearby points in higher dimensions. So the solution should model small distances accurately. That is, moderately distant data points will have to be placed too far apart in the map. So t-distributed stochastic neighbor embedding, it alleviates the problem of SNE using a different cost function. So the cost function is symmetric because it uses joint probability, and because of that the gradient calculation is simpler and faster, and it uses student t distribution instead of Gaussian in lower dimensions. So in higher dimension it uses Gaussian, and in lower dimension it uses student t distribution. So this helps in solving the crowding problem, and we use student t distribution with degree of freedom equal to 1, and this is also known as Cauchy distribution. And t-SNE models dissimilar data points by large pairwise distances and similar data points by small pairwise distances. So let's have a look at the t-SNE algorithm. So the first step is same, that we find the probability that xj will be a neighbor of xi. Then we compute the joint probability Pij, that is p of xj given xi plus p of xi given xj divided by 2n. And since this is symmetric in nature, that is P of ij is equal to P of ji, we'll have to do less computations, and P of ii is equal to 0. Then again we set some initial solution with some random values, and here again the n is less than or equal to 3. Then we repeat for several iterations, for example 1000 iterations. So first we compute the joint probability Qij, and this time we use the student t distribution. Then we compute the gradient d. Again, the cost function is sum of Kullback-Leibler divergences, but the equation this time is different because of joint probabilities and student t distribution. And then we update the solution using the same equation that was in SNE. These are some references. So the first one is the original paper for SNE. The second one is the original paper for tSNE. And the third one is the Wikipedia article for tSNE. I would also like to mention two more links. So first one is the tSNE's author's website. So there he has listed several implementations of the algorithm in different programming languages, and also has some FAQs related to tSNE which you can read. And also the second one is the Python implementation of tSNE by Adam Oruku. And you can also read this this article in case you want to implement the algorithm yourself. Thank you for watching this video and hope you found this video informational.